You clicked because KUKA's multi-axis robots look hypnotic in every marketing video. But that visual dexterity hides a critical stability problem that stops real-world automation dead in its tracks. By the end of this explanation, you will understand why adding extra degrees of freedom creates a maintenance nightmare rather than just more speed. The gap between smooth simulation and chaotic reality is where your production line dies, not from lack of power, but from mathematical failure. Let us start with what actually happens when engineers add that seventh degree of freedom to a standard six-axis arm on a linear rail system. You have now created a kinematically redundant manipulator, which sounds like an engineering upgrade until you realize it introduces infinite possible ways for the robot to reach any single point in space. The marketing calls this hypnotic dexterity because the end effector can move around obstacles with fluid grace that a standard arm cannot match. But behind that smooth motion lies a control problem so complex that solving it requires algorithms far more sophisticated than simple inverse kinematics. The core issue is what engineers call singularity avoidance. When you have 7 degrees of freedom in a 6-dimensional workspace, the robot must constantly decide which redundant path to take while avoiding positions where all joints align and lose rotational power. If the control software fails to resolve this redundancy instantly, the system does not just pause. It can enter a state of oscillation or lock up entirely under high-speed conditions. This is why the very feature that gives you extended workspace becomes your biggest liability when things go wrong at production speeds. Now consider the computational overhead required to keep these systems stable in real time. Every single millisecond, the controller must calculate the Jacobian matrix and apply a damped least squares method or null space optimization to determine the safest trajectory. These mathematical operations consume significant processing power that standard industrial controllers were not designed for. The result is often a bottleneck where the robot slows down just enough to keep its internal math stable, effectively killing the high-speed advantage you paid extra for in the first place. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the thing most automation engineers miss about these systems. You are trading visual spectacle for computational latency. When you deploy a 7-degree of freedom system on a linear axis, you introduce compounding error sources that do not exist in standard 6-axis setups. The precision of the base arm must be constantly calibrated against the straightness and repeatability of the rail itself. Even a minor drift in the linear track can render your sophisticated redundancy resolution algorithms completely ineffective because the mathematical models no longer match physical reality. This calibration challenge means that what looks like a stable robot on day 1 becomes an unstable beast by month 3 if maintenance is not rigorous. Practitioners note that managing this redundancy requires deep expertise in kinematics libraries rather than standard robotic arm programming skills. You cannot simply plug these systems into existing workflows and expect them to work out of the box. The software ecosystem relies heavily on custom implementations using frameworks like ROS2 or MoveIt to handle the extra degree of freedom, creating a significant barrier to entry for generalist automation engineers who lack this specialized background. The gap between theoretical kinematic solutions and real-world deployment remains a known hurdle that many buyers overlook until it is too late. While simulation tools allow you to see smooth motion in a virtual environment, they cannot fully replicate the mechanical imperfections of physical rails or the thermal drift of motors under load. When the robot encounters an unexpected obstacle or slight variation in payload weight, the redundancy resolution must adapt instantly without causing kinematic singularities that could damage hardware. Failure to resolve these singularities does not just cause a software error log. It can halt operations for hours while technicians manually recalibrate the entire system, or worse, it causes mechanical stress that leads to premature wear on joints and gears. The computational overhead required to prevent this means you are running your controller at near maximum capacity constantly. This leaves no room for safety margins when production demands spike or environmental conditions change. The reality is that high-speed multi-axis dexterity comes with a heavy price tag in terms of system complexity. You are essentially paying for the ability to solve an underdetermined problem in real time, which requires constant vigilance and specialized knowledge. Without this expertise, you risk turning your production line into a source of downtime rather than efficiency gains. The hypnotic movement is just a visual illusion masking a fragile control structure that demands perfection from both hardware alignment and software logic. This brings us to the critical insight that changes how we view these systems entirely. The dexterity itself is not the problem, but the assumption that redundancy equals flexibility without cost is what fails in production environments. Every time you add a degree of freedom, you multiply the potential failure modes exponentially rather than linearly. A standard 6-axis robot has one path to most points. Your 7-degree of freedom system on a rail has infinite paths, and choosing the wrong one at high speed can cause catastrophic collision or mechanical binding that no amount of software optimization can fix once it happens physically. The maintenance burden is not just about cleaning filters or checking lubrication. It involves continuous verification of kinematic models against physical reality to ensure the robot does not drift into a singularity during operation. This requires specialized tools and deep understanding of how redundancy resolution algorithms interact with mechanical tolerances in real time. If you do not have this capability in-house, your high-speed investment becomes a liability that drags down overall equipment effectiveness rather than boosting it. The engineering rigor required to maintain these complex systems in production is the true differentiator between success and failure. It separates companies that can leverage advanced robotics from those that get burned by overpromised capabilities. The hypnotic factor fades quickly when you are staring at a halted line trying to debug why your redundancy resolution algorithm chose a path that led directly into an obstacle because of a half-millimeter rail drift. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.